Okay, so part two of chemistry. Um, where we left off is we were talking about how water is a polar molecule, right? So, meaning that the oxygen and the hydrogens do not share their electrons equally, right? So, the next thing we're going to talk about is we're going to talk about why water is so important for life, at least life on Earth, life as we understand it. Okay, so let's talk about that a little bit. So, um, the part that I think kind of goes without saying is that life started in water, right? You know this because we were talking about this when we talked about the origin of life quite some time ago, right? Life started in water, and life stayed in water for millions and millions of years, right? It wasn't until, I don't know, a couple 100 million years ago that, is that right? Right. Anyway, until life actually came out onto land. Okay. So, anyway, life started in water. So, water is super important for that reason. Okay. But there are several other characteristics of water that are really important for living things that are interesting to think about from a chemical perspective, right? From the perspective of the um, polarity of water molecules. So here's one. Water exhibits three different characteristics that are related. They're not identical, but they're related. Cohesion, adhesion, and surface tension. All three of these things. So cohesion means that water molecules stick to each other. Okay. Adhesion means that water molecules stick to certain other things like glass, for example. Surface tension is just the term that's used to describe the fact that water, the surface of water, because water is so cohesive, water molecules stick to one another. Water almost has like a skin on the top of it. And so all of these things you're probably familiar with, but you might need to be sort of reminded. And all of these things relate to the fact that water forms hydrogen bonds. So we talked about that at the end of the last video, what hydrogen bonds are, okay? So water molecules are attracted to each other, right? So they're kind of sticky. That's what cohesion is about. Why is this important? Who cares? The whole way that water moves through plants is based on cohesion, right? So plants don't have a pump like a heart, like animals do. Many animals, not all animals, but many animals have a heart or some sort of pump to pump fluid through our bodies. Plants don't have that. So how does a plant, let's say we're talking about a tree that's a couple 100 feet tall, how does it move water from deep underground all the way through the tree up to the top of the tree to the leaves, right? It's a result of the fact that water is cohesive. Water molecules stick to each other. So as water evaporates from the leaves at the tips of the branches, right, it pulls the water molecules behind it because water molecules tend to stick together. So that's cohesion, right? And that's a pretty important feature for life, okay? Um, this high surface tension is kind of another example of this idea of water being cohesive. It's the same concept, just a different name. Um, there are many organisms that spend their life on the surface of water. So if you've ever seen a water strider, that's this insect right here, or some spiders, they spread their body weight out over enough area and they can actually walk across the surface of water, even though their bodies are more dense than water. So they should shrink because of the surface tension of water. They can kind of sit on top. And so this is something that you can like test at home if you want to play with it. Get yourself a glass of water, right? And just pour water in the glass. And if you have a real steady hand, you can pour it so that the water is actually above the rim of the glass and it doesn't spill out. And the reason that it doesn't spill out is because the water molecules are attracted to each other and it will actually like form this like I said, like a skin, right, on the surface. You can also get small things, small light things to float on the surface of water, even if the material is more dense than water. So paper clips, for example, a paper clip is metal, right? So if you don't put it in carefully, if you just drop it in a bottle of water, in a cup of water, it'll just sink to the bottom. But if you're really, really delicate and you gently place it on the surface, because of the surface tension of water, if you don't break that surface tension, you can actually get it to stay. This is the reason why it hurts so much when you when you have a belly flop into a pool, right? Because essentially, yeah, if you hit the water from a high distance, you don't just easily go right through it because of that surface tension, right? And that's what you're hitting. Now, eventually, your body weight breaks through that surface tension and then you sink. But the reason that you get that you get pink, right, that you turn red when you have a belly flop, is because you actually hit that water pretty hard and you hit that surface tension. Okay. This little guy here is one common name for this animal. They call it a basilisk lizard, but the other nickname it has is people call it a Jesus Christ lizard, because these guys can actually run across water without sinking. They can walk on water. Part of it is their speed, but the other thing is their toes are all spread out so they don't break the surface tension when they run. So anyway, so surface tension is another pretty cool trick that's useful for a lot of living things, right? That live in or on water. Okay. So cohesion, adhesion, surface tension. Another characteristic that's really unique is the fact that ice floats. Now, this is kind of a cool trick, and we'll talk about why it's important for life in just a second. Okay, so first, let's look at these two pictures. So these two circles are the same exact size. I'm not going to do it right now, but if you wanted to, okay, if you wanted to, I was about to sneeze, you can actually count the water molecules and see that there are more water molecules. Pen's not working. There we go. More water molecules in that circle, which contains liquid water, than this one, which contains solid water or ice. Okay. So why does ice float? Well, ice floats because it's less dense. And the reason that ice is less dense than liquid water, this isn't true of all solids and liquids, right? The reason that ice floats is because in order to form the stable crystalline structure of ice, the hydrogen bonds are more permanent, right? They're not permanent because it can melt, of course, but they're sturdier, right? They're sturdier hydrogen bonds, and so they're more kind of spread out from each other. Whereas when you have liquid water, I got a new water bottle since the last video. When you have liquid water, those bonds are constantly breaking and reforming. So liquid water is more dense. This is why if you put ice in liquid water, the ice will float. Okay, now, why is this important? Why do we care other than that it's entertaining? Because ice actually acts as an insulator. So when you have, good-sized bodies of water, like a lake, for example, that are in places that freeze, right? The top layer of the water freezes and becomes ice, which stays floating. It doesn't sink, right? And it acts like an insulator so that the water beneath stays a liquid, right? So fish that live in lakes, even if those lakes are in a super cold place and it is freezing, like freezing outside, right? The top part of the water turns to ice, but beneath that it stays liquid, and that allows living things to survive, right, through winters. The water is slightly warmer below that because it's insulated from that ice. Yeah, pretty cool actually, right? What else? Water has a very high heat capacity. This is probably the hardest thing to explain. So you can kind of understand what hydrogen bonds have to do with this and this, right? It's pretty, I don't know, it's pretty clear, I think. But it's harder to understand the high heat capacity of water. So what does that mean? What it means is that water can absorb a lot of heat energy before its temperature changes. Temperature is essentially a measurement of energy. It's like stored energy, basically. And so water molecules, because it has these flexible hydrogen bonds, can absorb a lot of heat and then release it slowly, right? Much more so than air, for example. Okay. I have all kinds of illustrations of this that you can imagine. Some of them involve our, local beaches and the desert, right? So, good example, you go to the beach. Let's say you went to the beach in the late summer, early fall, right? It might be 85 degrees during the day, maybe 75 degrees at night, right? The air temperature. It's pretty mild. There's not a huge temperature change at the beach between daytime and nighttime. But if you go to the high desert on that same exact day, and it's really not that far away. I mean, it's a bit of a drive, but it's, thinking like globally from a global perspective, it's not that far away. What would we be looking at there? Well, we'd be looking at, maybe 95 degrees during the day, right? And, maybe 60 degrees at night. Much bigger swing temperature change, okay? And a lot of that has the fact to do with hold on a second. My kiddo is watching Netflix in here with me, but he's got like headphones on so that you can see it in the background. But anyway, you can't hear him. And he just had to announce to me that he was watching a TV show called Absurd Planet. Is that what it's called, honey? And he's watching a clip about a kind of fish that lives inside of a sea cucumber's butt. Anyway, I'll report more later.
For your next assignment.
He's like, yeah, totally use that for assignment. Anyway, as we were talking about water. So let's go back to the beach. All right. Well, at the beach, the reason why you have such a small swing between daytime highs and nighttime lows is that there's a huge body of water, right? So during the day, the water absorbs a lot of the heat from the sun without changing its temperature very much. And then at night, it releases that heat so that it doesn't get as cold as it would in the desert, where in the desert, right, there's not as much water. So there's nothing to kind of absorb heat during the day. So it's just hot, 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 hot. And there's nothing to then release that like stored heat, right, at night. So that's high heat capacity. Okay. This is also the reason that we sweat. So I don't know who this guy is. This is a picture from your book. I can see that he is a football player. I don't watch so much of the football, but look at this man steaming, right? So clearly, he's sweating, right? And it must be cool where he is because you can see the water vapor like evaporating off of his body. So why do we sweat? Why does that keep us cool? Well, the reason that sweating keeps us cool, once again, is this idea of high heat capacity. So when water is evaporating from your body surface, it takes heat with it because it absorbs so much heat, right? And so this is the same reason that dogs pant, right? The reason that a dog pants, right, is they're getting rid of water vapor because water carries heat with it and actually cools your body down, okay? Whether it's sweat, whether it's panting, whatever. You can actually tell, right? So, the next time you're doing something sweaty because, it's hot outside or you're exercising or whatever, find a place in your body that's sweating a lot, but is also exposed to the air. So like your cheek, okay? Next time it's a super hot day and you go outside for a walk, right? Put your hand on your cheek and you can tell that the area where the sweating is happening it actually feels a little bit cooler to the touch, right? High heat capacity. So that was the third one, right? So adhesion, cohesion, surface tension, ice floats, high heat capacity. The last one is water is an incredible solvent. I don't believe we've used this vocabulary before, so excuse me if I repeat myself, but the terms solvent, solute, solution. Okay, so the terms solvent, solute, and solution. A solvent is the dissolving medium. So it's the stuff that you're dissolving something in. The something that you're dissolving is called a solute. So you guys did this with Alka-Seltzer, right? In your Alka-Seltzer lab, the solvent that most of you used was water, right? Some of you used funky things like tea and, Gatorade and soda and juice and whatever. But for the most part, most of you used water as your solvent. Your solute was the Alka-Seltzer, okay? Once those two things are combined, we call it a solution. This is going to come up again in labs, so make sure you're familiar with that vocabulary. The reason that water is used as a solvent so much is that water is an amazing solvent. And the reason that water is an amazing solvent is because water molecules are polar. So remember this idea about Mickey's chin being slightly negative and Mickey's ears are slightly positive? What that means is that any substance that has a charge to it, like, for example, our sodium chloride. Remember how sodium chloride is a compound that is formed from ionic bonding, right? Well, you put salt in water and what happens? It dissolves pretty quickly, actually, right? And the reason that it dissolves is those positive sodium ions are attracted to Mickey's chin. See all the Mickey chins surrounding it, right? And the negative chloride ion is attracted to all the Mickey ears, right? Because they're slightly positive, yeah? So tons of things. Anything that has a charge or is even slightly polar easily dissolves in water. Any really small molecules dissolve easily in water. The only things that don't mix very well with water are things that we typically refer to as lipids. We're going to come back to that in a few minutes. Spoiler, okay? I'm going to leave you with a little cliffhanger because we'll come back to lipids in a bit, okay? So that, oh my gosh, the interruptions are strong today. Let's pause again. I can't remember. Sorry, there was an interruption. I forgot where I was. Anyway, so water is an amazing solvent. And fundamentally, to kind of circle back to what we started with at the beginning of the video, is the reason that life started in water is because so many things can dissolve in water, right? Chemical reactions happen abundantly in water, right? So it's just, yeah, right. It's super important for life. So all of these different characteristics are all super important for living things. Okay. All right. The last little topic we're going to talk about in this segment of the video is pH. I don't want to get into the weeds too much with this. Basically, what pH is, it's a measure of how many hydrogen ions, right? So H plus, right? Those are hydrogen ions. Of how many hydrogen ions are in a solution. So things that we call an acid have increasing, right? The more and more acidic something is, the more hydrogen ions it has in the solution. The more basic something is, the lower the number of hydrogen ions that it has. One sort of common misconception is people think about acids like burning stuff, right? Which is true, yeah? So like you don't want to get battery acid on your hands, right? For that matter, lemon juice hurts like a son of a gun if you get it in a boo-boo, right? Or it's like you have a little sore in your mouth or something and you get lemon juice on it, yeah? So acids can damage your tissues because those are strong acids, yeah? But so can straight. So lye and bleach and ammonia are incredibly corrosive, right? So plug that back in, bud. So they're incredibly corrosive. So both strong bases and strong acids can cause damage to tissues. There are some examples of some the pH of several different things, just to kind of give you some some framework. So your blood is slightly basic. One thing that's kind of interesting that it always kind of simultaneously makes me feel sad and a little bit annoyed is whenever I see people talk about drinking alkalized water or having a very strongly alkalizing diet. Oh, you need to consume things that are alkaline. Alkaline is another name for basic. Okay. Um, don't spend extra money on water that is alkaline, because we have systems in our body that exist specifically. The whole reason they exist are specifically to maintain the pH of our blood at 7.4. So essentially what you're doing when you're drinking alkalized water is just making your kidneys work harder at maintaining your pH. Now, it doesn't hurt your kidneys. It's not going to hurt you, right? But you're not actually alkalizing anything because your body just works super hard to keep your pH the way that it's supposed to be. So don't fall for all that alkalizing business, right? If you like the taste of certain bottled waters more than other bottled waters, whatever. I mean, you do you, okay? But this whole idea of alkalized water is 100% pseudoscientific BS. Totally, totally BS, right? Because no matter what you drink, right, whether it's super acidic or super basic. I mean, if you drink something that's super acidic or super basic, you're going to, corrode and eat your stomach lining. But, right, alkalized water is like, 7.6 or 8 instead of 7, right? And your body's just going to immediately convert that to what pH your blood is supposed to be. Okay. So don't waste your money on that stuff. All right. Tell your friends, stop wasting your money on alkalized water. Okay. Anyway, so that's pH. All right. So, like I said, we're not going to get into this too much. I just kind of wanted to mention it because it's, it's a thing that comes up. We sometimes you have, there are these chemical substances called buffers. And what a buffer is something that kind of keeps the pH of something from swinging too much, right? In case you're, wondering what that is. But honestly, that's all I'm going to say about pH. Okay. So just to kind of recap these first couple sections, chemical reactions. We talked about what reactants are. Those are the things that are what you start with. The products are what you end with, right? We talked a little bit about how to read them. Most chemical reactions happen in water because water is such a good solvent. Okay, that's why your body's mostly water. That's why you need to stay hydrated, no matter what kind of water you're drinking, right? You need to stay hydrated because, right, that's how chemical reactions happen inside of your cells, is that you have plenty of water there. Okay. So anyway, so that's that. Okay. Right. So I think I'm going to stop here because this is a good sort of stopping point. Okay, the next thing we're going to talk about is we're going to talk about molecules of life. And I think I'm even going to break that up into 2 videos just so it's not too long. Okay. All right. So the next one will be on macromolecules, or the molecules of life.